Hey guys, welcome to the final lecture of the Physics Engine course as promised in a video format. Today we'll pick up where we left off last week and finish our contact resolution system, thus bringing our rigid body physics engine and as a result our entire physics engine to its conclusion. There were obviously rooms for improvement and a few places, in fact quite a few places, where our physics engine wouldn't hold very strongly. And I'll talk about a few of those towards the end of the video, but know that there are definitely rooms for improvement. In fact, if you are interested in learning about what possible improvements could be made, there is a chapter in the book dedicated to that, and since we followed the book pretty closely for our implementation of the physics engine, most of that holds very true for our engine as well. But yeah, for our purposes, we will actually have a fairly robust physics engine by the end of this lecture. Two quick notes. Unlike our regular lectures where I write the code along with you guys, I have already prepared everything for this lecture because I kind of felt it's pointless me writing code in a video. So everything that I'm going to talk about today is already written, and you can find the code on GitHub. So if you're wondering, where you'd find everything that I'm talking about, it is on GitHub. If you want, you can try to go from where we left off last week, follow along with the lecture, and try to implement everything that I'm talking about yourself. But if you're not able to do that, you can simply get it from GitHub. So that's the first thing. The second thing is I highly recommend having the book open while you're going through this lecture, and I will be mentioning sections of the book that I have used for implementing the code. And when I do that, it is actually highly advisable that you pause the video, go to at least take a quick read through the section and maybe look at it later after the video in detail, but definitely pause the video, take a look at the section, and then get back, and that way the code will actually make a lot more sense. And also, I'll only be able to explain so much in code. There are the actual physics behind it. You'll get a much better idea if you just read those particular sections of the book. All right, with that, let's jump right in. So let's go to our contact resolution system. This is what we were writing, or this is what we were doing in the last class. And you'd notice there is a small change here. So in the last class, in our update is where we had all the logic for resolving velocity. I have captured that in this function called resolve velocity instead of having all of that code in update. You'll also see something new, resolve penetration. That was not there last week. That's completely new, and that's one of the things that I'll be talking about in this video. But essentially what I've done is move them to their own function so that the update function itself is not really cluttered and it's easy to read. So let's go into resolve velocity. That's what essentially we were doing last week. Given a contact event, what will the final velocities of the two objects involved in the contact be? So the contact event, let me just quickly go there and show you guys what it is. We already did this last week, but again, just as a refresher. The contact event obviously holds the two entities that are in contact. This is like our particle contact resolution as well. Since we are using an entity component system structure, we do not want to pass reference. So this is pass reference to the rigid body itself. Not the best way to do this, but this is the more efficient way to do this because of our entity component system. So we directly give the entities themselves within this contact event as opposed to a reference to the rigid bodies or something like that. So we have the two entities, the normal, the normal from A to B for the collision, the penetration depth. All of these are, they're there for particle contacts as well. Something slightly different is there are 2 points of contact as opposed to one, and in fact, we have the position of the point of contact in local space of each object and then as in world coordinates. Now, because when two rigid bodies are overlapping, it's rarely the case that they're going to overlap exactly at one point. It's more likely the case that, in fact, we know they will be penetrating, and that means there are actually infinitely many points which are overlapping within those rigid bodies, but we actually pick like two best points, the two extreme points of that contact, and store those as point 1 and point 2, and then have their local coordinates and their world coordinates. So that's why we have 2 points. And if you actually run I think there's a function in main, let me just quickly look it up. I think it's called test contacts. If you run that function, you'll actually see. So that function, in fact, you can actually run test collision as well without penetration. My point is you can actually see what these 2 contact points are. Anyways, and then finally it holds the restitution, which is the energy loss due to a collision. Restitution of 0 means all energy is lost. Restitution of 1 means no energy is lost. It's a perfectly elastic collision. So that's what our contact event holds. So back in our contact resolution system, let's see what we're doing with this contact. So first we make a few variables to cache the rigid body component and the transform component of the 2 entities involved in the contact. Ideally, I should be checking if each of these entities have these components on them, but for now I'm just giving that check because we should always make sure that they do in fact have rigid body and transform at least. Okay, like I said, since there are 2 points involved in the contact, I actually thought it might be, at least as a starting point, it might be just have a contact point which is the average of the 2 points, but later on you'll see I'm actually not using that, so this is not even important. The first thing we do is actually calculate a coordinate system which is local to the contact point. That's because the restitution itself is along the normal, and a lot of the things that we'll see, impulse and in fact impulse is the main thing, are much easier to express along the normal than in world coordinates. So we actually make a coordinate system which has the normal of the collision as the x-axis, and then y and z could be chosen arbitrarily, and then do all the math, all the math and the physics in that coordinate system, and then finally just extract the result out and put it in our world coordinate system. So that's what we have done. We have an arbitrary y and z axis, and more importantly, a mat3, a 3x3 matrix, which is the transformation matrix from that coordinate system to world coordinates. After that, we calculate the relative positions. So that is the radius vector of each of those contact points from the corresponding object's center. And then, before I continue, quickly, the section of the book where all this is explained is actually the first section of chapter 14 all the way up. So 14.1 and 14.2 and all their subsections. So at this point, I would actually recommend, before you continue, go through 14.1 and 14.2, which is where the book explains all the logic that we will be implementing in this velocity resolution. So once you've done that, you'll see that, so we first need the relative positions, and then there are inertia tensors. So this is making sure that, inertia tensors for each rigid body is in their local coordinates, so we get the world coordinates. What do we do after that? First, we calculate the top. So the idea here is that since we don't know what the impulse is for this collision, that is what we're trying to calculate. Once we know the impulse for the collision, we can calculate how much velocity change and rotation change it will generate. Since we don't know that, we do a slightly roundabout way of calculating that. Instead of going directly from the physics equations and calculating the impulse, first we actually calculate the velocity change that would be caused by a unit impulse. So if there was an impulse literally of magnitude 1, what would be the change in velocity that would introduce, both in for both the objects, basically. And then once we have that, we can calculate what is the actual change in velocity that we need. That's because of restitution. That just simply tells us, given incoming velocity, what the outgoing velocity should be. So now that we have what the actual outgoing velocity should be and how much the outgoing velocity would have been given 1 unit of impulse, we can calculate what the impulse actually is. And once we have that, then the problem is basically solved. So for the first few steps, we are assuming that impulse is 1. What does impulse of 1 mean? That means there is a force of magnitude 1 along the contact normal, because impulse in a collision is going to be along the contact normal. Contact normal is already normalized, so that is the force that we're experiencing if the magnitude is 1. If you guys remember, torque is R cross F, so relative position times force. Force is contact dot normal because we're saying it's a force of magnitude 1 along the normal. So that's how we get the torque. From torque, we get the angular velocity. We're calling it rotation per unit impulse. This is basically angular velocity. Angular velocity is I inverse times torque. Inverse moment of inertia tensor times torque. And then finally, velocity is R cross omega cross R rather. Yeah, so velocity is omega cross R, omega being angular velocity and R being relative position. So that's basically that's what we're doing in 3 steps. First calculate torque, then calculate the rotation that will introduce, and then the actual change in velocity because of that rotation. So with that, we get the delta velocity for the first object. And note that this delta velocity that we're getting, that's right now in world coordinates. So we take a dot product with the normal to convert that into local coordinates. And even with that, that just tells us what the change in velocity is due to rotation. This change in velocity comes purely from torque. So this is the rotational change in velocity. We do have to add the linear change. The linear change is just inverse of mass, because linear change in velocity is impulse divided by mass, essentially. So but we have to make sure that we add that as well. So it's angular plus linear. That's the net change in velocity of object A. I'm just calling it delta vel instead of delta vel A because we'll do the exact same thing for B and just add to it, because we are trying to calculate the total change in velocity in object A and B, not just one of them. Once we have that, so remember, this delta vel that we got over here is what the change in velocity would have been if the impulse just had a magnitude of 1. The next thing is to calculate what the actual velocity will be. So for that, first we need to calculate incoming velocity. That's pretty straightforward. First you calculate the velocity due to rotation. Like I said, velocity due to rotation is angular velocity times the cross product of angular velocity times the radial vector omega cross r, and then the linear velocity is just the rigid body's velocity. Same thing for object B. Then we calculate the closing velocity as velocity of A minus velocity of B. If you remember, the coefficient of restitution of a collision is basically the ratio of outgoing versus incoming velocity. So from the closing velocity, of course, we do want to make sure we convert that to the local coordinates. We are doing everything in our contact coordinate system. So whenever we calculate something in world coordinates, we do have to make sure we calculate it in the local coordinates, the coordinates in which you're checking. And in that local coordinate, we now know that the incoming velocity is its component along the normal, and the normal is the x-axis. So its component along the normal actually becomes really straightforward. It is the x component of this incoming velocity, or this closing velocity. If that's less than 0, that means the objects are already separating. We don't need to worry about it, so just return. Otherwise, we can calculate what the desired velocity, the outgoing delta velocity should be based on restitution. And then once we have that, we had the delta vel, which was the velocity change due to 1 unit of impulse. We have the desired change in velocity. Then the actual impulse just becomes desired velocity by delta velocity. Note that we are only doing it in the x-axis because we know that the impulse will be along the normal. So this magnitude of impulse will be all along the normal, and since this is in the contact coordinate system, that just means it is that value in x and the other two coordinates are 0. And this is why we did everything in that coordinate system, so that it's all very easy up to this point. But once we get the impulse in the local coordinate system, now it's time to calculate that in world coordinates and actually use that to calculate the final outgoing velocities. So that's pretty easy. We already had that matrix which stored, where was that? So right at the beginning, we had that matrix which stores the transformation from the contact coordinate system to the world coordinate system. So we just multiply with that matrix to get impulse in world coordinate system. Now here, I'm calling it impulse A because along x-axis, we do everything. The normal is from A to B. Relative velocity is velocity of A minus velocity of B. So the impulse we're getting here is actually the impulse experienced by object A. Object B just experiences an equal and opposite impulse, so that's why it's just minus impulse A. Once we have impulse, now it's time to calculate the change in linear velocity and rotational velocity. Now, linear velocity is very simple, so we'll do it in step first for A and then for B, and then the calculations are exactly identical. So velocity change is pretty simple. It's just, so force is mass times acceleration, impulse is mass times velocity, delta velocity. So velocity change is simply impulse by mass. For the rotation, however, we need to calculate, so rotation is stored as a quaternion. So we need to calculate what, actually, that's not what we're trying to do here. Sorry, I was talking about penetration. Here we are just trying to calculate the change in angular velocity. So this is actually pretty straightforward. So first we calculate torque. Again, so torque is R cross F. Here in, so I guess I should have really called it inertial torque as opposed to torque due to a force. So torque is R cross F, inertial torque is R cross impulse. So the radial vector cross product with the impulse gives us the torque. From torque we get velocity change, just like I said, I inverse times torque. And from that, we just add that to the angular velocity. We have velocity change and angular velocity change. We just update the velocity and the angular velocity by that amount. Do the same thing for object B, do some debug drawing, and that's it. That's our velocity resolution. If you guys remember, we did almost exactly all of this last week, but we had a problem. We had a problem where our cube was not bouncing the way we wanted, or bouncing the way that would have looked logical. It felt like it was gaining energy as opposed to losing it due to the collision, and even if the coefficient of restitution was less than 1. So that was happening because of a really small error where I was calculating the torque as the cross product of impulse and the rate. So I was doing it as impulse cross rate or relative position, whereas it should be relative position cause impulse. What is happening is changing the order in a cross product makes it negative of what it would have been otherwise. It changes the sign. What that meant was, instead of after collision, instead of the object rotating in the opposite direction, it was rotating more in the same direction, essentially adding more speed rather than taking it away. And that's why it looked like it's gaining energy. So that was the error that you needed to fix. Actually, that was the reason why it looked like it's gaining energy. There was another small thing that I fixed, which is the inertia tensor itself. When we wrote our rigid body, I don't know if you guys remember. Let me quickly go to my rigid body component. There we go. We had hard-coded the inertia tensor to some value, and that was fine before we had colliders. But once we have colliders now, the shape of the collider is what determines what the inertia tensor should be in the first place. So hard-coding it would not give very realistic results. Instead, what I did was I changed it so that when you create a rigid body, the default value of the inertia tensor is almost negligible. It's not 0, because that might cause some not a number errors. In fact, ideally it should be 0, and those should be dealt with separately. But for now, I have just assigned a default value of really negligible inertia tensor, and then every time you add a collider, so let's go to box collider. Every time you add a collider, the collider updates. Actually, not every time you add it. At every frame, the collider updates the rigid body's inertia tensor with its own, with what its contribution is going to be. So the collider now takes care of adding the inertia tensor correct to its dimensions. And I do the same thing for sphere colliders as well. That was the other reason why the bouncing did not look right. So with this, before we go into penetration, let me show you guys what this will look like. So that's pretty easy. That's why these are two separate functions. I can just comment out resolve penetration and hit play. I modified where the boxes and all that were spinning. So last class we only had a sphere and a box. Now I have a couple of other things. So let me just play and let's see what it looks like. Alright, sorry, yeah, I had to switch the windows on my OBS, which is where I'm recording, and it's a little laggy because I think recording while I'm doing this is too much for my laptop to handle. Anyway, so you can see there are a bunch of spheres and a bunch of cubes. You can see that some of them are, I'm spawning them randomly, so some of them already have contacts. Since there is no penetration algorithm, they're not getting resolved. So if I play this, it happens very slowly. Actually, that's a little too laggy for my taste. Let me see if I can fix that. Maybe if I close Steam, this will run better. Let's see. No, that was not it. I was not actually thinking Steam has anything to do with it. That was the only other thing I have running other than OBS. I guess it's just laggy because I have something else open. Because, yeah, I was getting a solid 60 frames, and it still says I'm getting 60 frames per second, so I'm not really sure what the issue is. But, yeah, that is what it looks like. Let me actually reduce the number of boxes to show what the collision actually looks like. And then I'm sure you guys can have the number as high as, I think I have 40 right now. Yeah, so I'll put that to a 10 and see what that looks like. But you guys should be able to see, if you download the project from GitHub, you should be able to keep it at 40, and because at any point there are only so few contacts, it shouldn't lag a lot. All right, let me make sure you guys can actually see it. Let me quickly switch to, yeah, there you go. So yeah, so that's a lot fewer. If I play, this is what it looks like. And this itself already looks okay, even though we don't have any sort of penetration code. This looks okay. I don't know if you guys can tell, there is definitely a little bit of lag still. And I can notice that. But yeah, this is what it looks like. Already looks serviceable. Now, if I let this sit for a very long time, objects will actually start sinking into the floor because there is no, first of all, there is no penetration check, and then there's also no resting contact. But the actual velocity resolution itself looks fine. So yeah, so that's the velocity resolution part. Now let's move on to penetration resolution. Like I said, right now, if you let objects sit on the floor for too long, they will start going into it. And also, there is really nothing preventing objects from going into each other in the first place. So for that, just like we had for the particles, we have to resolve penetrations. Every time two objects are penetrating into each other, we have to move them so that they're not penetrating anymore. Now, you'd think that the solution should be really straightforward. We should just do what we did for particles and just move them back along the normal in the ratio of their masses. And you could actually do that. In fact, for this, I would recommend reading sections Section 14.3, resolving interpenetration. So I would say definitely give that a read before going through the code, and that explains why we can't just do what we did for particles. Essentially, the problem is objects are not just moving linearly, they're also rotating, so the penetration need not have happened just due to movement. It could have very easily happened for something which is almost stationary but is stationary as in not moving linearly but is rotating, and the rotation made it penetrate into another object. So that's why if we just push it back, that means we're compensating for a motion which might or might not have had anything to do with the penetration to begin with, giving pretty weird results. So instead, we want to resolve the penetration, we want to both move the objects, just like we did for particles, but also rotate them and find a good balance between both. Now, the way the book recommends doing this, and I actually find that approach really interesting, is instead of thinking of penetration as an error due to our fixed time step, think of it as two objects are actually pushing into each other, causing deformation, and to resolve that deformation, they have to apply an opposing force so that they're not deformed anymore. And what that means is we can actually convert this whole resolving penetration problem to another, if not velocity change, just like velocity change, calculate an impulse which will cause the penetration to become zero and bring all the equations that we used for resolving velocity. So the first bit is essentially the same, relative position, world inertia, tensor, and all of that. And then what we will do is basically calculate the total inertia of each of the objects, or rather the total inertia of both the objects. Remember, inertia is, the definition of inertia is the resistance to motion. And the simplest form of inertia is just mass. The heavier an object, the more its inertia. In fact, if we didn't have rotation, the only inertia will come from mass. If we have a combination of rotation and linear motion, inertia comes both from the angular and the linear part. So that's the first thing we're calculating. Calculating that is just like what we did with velocity. Inertia is r cross f. Again, we are assuming unit inertia. Actually, we are calculating inertia assuming a unit force or a unit impulse, and then just going through the same calculations, and then finally putting all of that in a total inertia as angular inertia plus linear inertia. Same thing with object B, and this total inertia, we use this to calculate how much each object should be moved linearly and how much each object should be moved angularly. Remember, the only difference between this or the main difference between this and velocity resolution is in velocity resolution, we ultimately want the physics to move the objects apart. So we only set their velocities, we don't actually move them apart. Whereas in penetration, yes, we are doing all of this, but this is more for us to have an easy way of approaching this problem, because otherwise how would you calculate how much an object should be moved and rotated by, how much both those objects should be moved and rotated by to resolve the penetration. This gives us an easy way of thinking, but ultimately our goal is to move those objects to those positions and angles as opposed to letting forces do that for us. So instead of applying the impulse to velocity and rotational velocity, we actually calculate how much the linear move and the angular move is. They're calculated as floats because we already know the directions in which you are going to move. We know that linear move is going to be along the normal, the angular move is going to be perpendicular to the normal. So we just calculate the magnitudes as floats. Then there's this little thing about a limit. So we do want to constrain how much this angular movement is going to be. This angular movement is the correction for the penetration. It is possible that this movement actually causes new penetrations. So we want to limit how much this angular correction can be. This is especially a problem is if two objects are penetrating a lot, because then turning one to resolve a penetration will most definitely cause some other corner of the object to actually cause a new penetration. So we definitely don't want that. So we just limit the angular movement in case it goes over whatever limit we have set, and then compensate for it by adding it to the linear movement. The artifact this will generate is it'll look like objects have friction where they shouldn't. Things will move, things will not rotate as, or rather, things will not move as much as you expect them to, because the linear move is pushing the object away from the penetration, not actually moving it. So if you add more to the linear move, it'll basically make it look like the object is not moving as much as it should. But we shouldn't hit this limit in the first place, because we shouldn't have very deep penetrations to begin with. Penetrations are an artifact of the fixed time step. But if the fixed time step is 1/60th of a second, we shouldn't have very deep penetrations. We should not have a long enough frame where two objects have penetrated a lot. So ideally, this should never be hit. This is just a safety measure in case that happens because of a frame rate drop or whatever. We do not actually end up causing a new penetration. And then finally, after all of that, we have the linear movement and the angular movement. We just move the objects according to those. Linear is pretty simple. We just set the position and the movement is along the normal, so we just move the two objects along the normal by their linear move amounts. The rotational movement, again, it's a little more involved. What are we doing here? Oh, so yeah, we calculate the torque, again, assuming unit impulse, and then how much the move would be due to that impulse. And then we already know the angular inertia, so then we calculate what the actual rotation is because of that. And yes, the rotation that we're getting, it's ultimately it's a vector, which is the angular velocity. The rotation or the orientation of a rigid body is stored as a quaternion. So there is one final step. Unlike the linear motion where we could simply add it along the direction of normal, here after calculating the rotation or the change in angle, we have to convert that to a quaternion. So basically, we have a quaternion. We want to rotate that quaternion by a certain angle. Then what is the resulting quaternion? So that's the math that we're doing here, and then finally setting the orientation to that quaternion. And that's it. We do that for object A and B, and we have the penetration algorithm. You might notice I actually have this multiplying the normal by 1. Yeah, I multiplied the normal by -1, and then I multiplied the normal again by -1 at the end. So I multiplied by -1 once at the start of the penetration algorithm, and then once at the end. That's because of a mistake I made. All the equations that I wrote are assuming the wrong direction for normal. Ideally, I should actually go in and change each of these contact dot normals to minus contact dot normal, or at least in some places. But what instead I end up doing is, since the effect is simply making, multiplying the normal by -1, I did that first to make sure the algorithm doesn't need to change, and then once the penetration algorithm is done, I just multiplied it by -1 again to make it its original value. Anyway, that's just a little shortcut that I took. But that's really it. We have a function for resolving penetration and a function for resolving velocity. And for now, I have kept it really simple. We just go through a list of contacts, resolve penetration, resolve velocity, and that's it. In our particle contact resolution, we actually did some sort of sorting where we always picked the best contact, then fixed its penetration and velocity, but that could have caused changes in penetration of other contacts if those same objects were involved in other contacts. So we actually went through and updated those penetrations and then ran the algorithm again, finding the best contact and all of that. We could have done that. In fact, if you read the book, it talks about how you can do that for rigid bodies, but I actually feel that is unnecessary for simple systems for the kind of stuff we're doing. And it's not the order of complexity that it introduces, it's not small. It literally goes from n to n square. So unless we really need it, we shouldn't actually worry about ordering. And in fact, we're doing a sorting every time we run an iteration, because once we solve a best contact, it might not be the best contact anymore. We are updating it, so we have to sort it every time. It just makes it n squared complexity. Not worth it unless you're seeing a problem. And this is what I was saying. Like, yeah, our engine does have shortcomings, but I think we can live with this for now. So yeah, I just simply update penetration and velocity for each object. So let's see what this looks like. So I'll run the same thing with the spheres and the boxes and see what that looks like. And for now, it actually looks almost the same. There's no noticeable difference. Like I said, if you keep this running, actually, I'm not even sure if you guys can see this in the video. Let me just make sure. Nope, you can't. Now you should be able to. Let me run this again from the beginning. My bad. Okay, this time let me make sure that it is actually capturing. Yeah, there we go. So yeah, like I was saying, if I run this, you won't be able to really see a difference. It looks the same. You would notice a difference if you let this run for a very long time. Now with penetration, objects will definitely not sink through the floor, which would be the case if it was just velocity resolution. And that's actually it. We have a simple but functional contact resolution. And like I said, this essentially brings our physics engine to a conclusion. I did say I will mention a few things about where the shortcomings are, what this engine can do, what it can't do. So first, the strengths of the engine is, it is very simple. It's very simple in terms of how it is resolving collisions, how it is resolving the contacts. It's not trying to go for the best contact at every frame, so it's actually pretty fast. And the downside to that is for contact situations where a single object is involved in multiple collisions. That's where this system wouldn't hold up very well. So remember the bridge demo, that was one of the assignments where we had each part or each particle on the bridge connected by a cable, then connected by 3, 4, or 5 rods. So each of those objects were involved in multiple collisions, and there were multiple of those objects. That is where a simple system or a simple collision resolution like this will completely break down, because the moment you try to solve one penetration, it'll change the other penetration, and since this will be happening every frame, they won't be able to sync up and your simulation will just blow up. That's where what we have written is bad. But for simple, unless you are really targeting for that, if your game is about making objects collide with each other and blow up and fall apart, this will do the job pretty well because most of the contacts in that case are disjointed, like what I was just showing you. Oh, I realize I actually don't have the code open. Again, my bad. But yeah, so it's good for situations where even a single object is not involved in many collisions. It's bad for situations where many objects are all colliding with each other on the same frame. With that, we are actually at the end of this lecture, but before I stop, let me quickly go over the assignment, which is the ragdolls. So this is not on GitHub, obviously, but I will quickly show you my code, or rather go over what I have done for ragdolls. So if you can see this folder, the ragdoll folder, the only two new things after having the collision resolution system working, the only things I would need is a joint component and a joint system. Essentially, a ragdoll is made up of these cubes which are connected to each other by a joint. So this joint is similar to our cable or our rod component. It doesn't generate any force. It just creates a contact when the rigid bodies involved violate that joint. So I'll show you what my joint component looks like. My joint component holds reference to the two entities that it's connecting, the positions, the position of where this joint should be on those entities, and I give a float epsilon, which is the error in the distance between the two positions for this joint. You should actually take a look at the section. I'm not going to go look at the book right now, but on the assignment, you'll see the section that I mentioned. It explains what a joint exactly is and pseudocode for that. Again, I've essentially implemented the same. But yeah, for us, it'll be a joint component and a joint system. Joint component has these variables. You could have slightly different variables, but essentially what information you need for the two objects that are connected by this joint. And you have to figure out the joint system, as in how it will generate a contact given these variables. But that's it. That's all you need for the ragdoll simulation. I'll go to my main. I made a make ragdoll function, which is where I'm doing this. All I did was I have all these different limbs on the ragdoll, right? The head, the spines, right? The arms, the legs, all of that. They are all just rigid bodies with box colliders. So let me actually go through the head. The rest of them are all the same with just different dimensions and offsets and or positions and all of that. But each of these limbs are a rigid body. They obviously have a transform component and they also have a corresponding box collider on them. And whenever I want to connect two of these, so let's say I have the head and very similarly I have the spine, then I have a joint, the head spine one joint, which is what has this joint component which connects the head and the spine with all the other parameters. So yeah, that's how you would go about implementing the ragdolls. All right, thank you for watching. I hope that was useful. Again, if you have any questions, message me on Discord. Have a good day.